Hi everyone, this is Akanksha and welcome to the fourth episode of our Mechanistic Interpretability 101 playlist. Today we are going to talk about Einsum and Einops. So as of September 2024, if you're interested in doing research in mechanistic interpretability, you will likely use a combination of these deep learning frameworks and these specialized tools designed for understanding and analyzing the internal workings of neural networks. So under frameworks, we have PyTorch and TensorFlow. Starting with PyTorch, it is widely used in research due to its flexibility and ease of experimentation. It allows dynamic computation graphs, making it easier to manipulate and examine the internals of a neural network. PyTorch lets us visualize and access layer outputs, gradients, and model weights, which is essential for probing the mechanisms of a network. And the other one is TensorFlow. It is also widely used in both research and production. It supports static computation graphs and has eager execution for more flexibility like PyTorch. It also includes TensorBoard for visualizing models and training progress, and it is ideal for scalable distributed training on GPUs and TPUs. So now, a key aspect of understanding the inner workings of a neural network is to be able to see what is happening at each step of the algorithm. And so, we use visualization and analysis tools like these listed here to grasp insights about how the neural network models are doing what they are doing. So, weights and biases here helps us track experiments, but it also offers features for visualizing activations, gradients, and internal metrics over time, making it useful for studying how a network learns and changes internally. This here, the Lucid library, which is TensorFlow based, is a toolkit for visualizing and interpreting neural networks, particularly convolutional networks. Lucid provides tools for generating images that highlight what neurons and layers focus on. Activation Atlases was based on this library. Similarly, Captum is for PyTorch, and it's a library built specifically for model interpretability in PyTorch. It provides tools for feature importance, gradient-based attribution, and other methods to explore why a neural network makes certain decisions. And this here, the Transformer Lens, is a Python library that was designed by Neil Nanda for doing mechanistic interpretability specifically on transformer models. It enables easy manipulation and exploration of the inner workings of a transformer. So it can be used for analyzing attention heads, identifying induction heads, and studying copying patterns within transformers. Don't worry if these terms are new to you. We will learn about all of these in the upcoming sessions. Along with these tools, Jupyter Notebooks and Google Colabs are widely used as they are excellent for interactive experimentation if you are just getting started. So all these toolkits basically allow our algorithms to play with our data. And when it comes to data, you might recollect from our linear algebra episode that data points are nothing but vectors. And these vectors are arranged in matrices for us to be able to do various transformation operations on the data. Now imagine stacking these matrices into 3 dimensions. That's a tensor. It holds data in more than 2 dimensions, and it is crucial in deep learning for handling complex data structures like images or video frames. So each of these basically is a building block for handling data in different shapes and sizes. By the way, if you want to learn and visualize tensors in a better way, please check a video that I will link in the description. I had particularly loved the explanation in that video when I was trying to understand tensors, and I'm sure it will be helpful for you too. So then, going back to the Mechanistic Interpretability Toolkit, both these libraries here, Einsum, which is short for Einstein summation, and Einops, which is short for Einstein operations, are designed to make tensor operations easy and efficient. So as you can imagine, all of our data is going to be stored as matrices or tensors, and doing a lot of transformation operations on them is going to get complex as we go into higher dimensions. And these libraries here are going to make our computations much more efficient. Einsum here is like a weapon in our toolkit for tensor operations. So instead of writing long, confusing code to do matrix multiplications or summing across axes, Einsum lets us express these operations in a single line. It's basically math or code, but more elegant. Imagine having the power to handle complex operations like matrix multiplication, dot products, or even tensor contractions with just one concise formula. That's the power of this library. We basically tell Einsum how the indices of the tensors interact, and it takes care of the rest. And Einops, which is short for Einstein operations, can be your go-to library for reshaping and rearranging tensors. Think of it as the artist of tensor manipulation. It allows you to perform complex tensor transformations with a clear, readable syntax. Einops makes operations like rearrange, reshape, or reducing tensors super intuitive. It is highly recommended using Einops to manipulate an individual tensor and Einsum to multiply tensors because not only is it simple to use, but also we have to spend less time debugging. Let us learn more about these from actual examples and see how efficient these libraries are. So before we begin looking into Einsum and Einops through examples on a Colab notebook, I wanted to take a moment and introduce you to the ARENA curriculum. So ARENA is basically this alignment research engineer accelerator program which runs in person, and you can access this link which I will share in description to learn more about it. But basically, Callum McDougall, who's now at Anthropic working into interpretability research, introduced this ARENA curriculum to help get people started in the field of AI alignment. So throughout our videos, I'll be referring to some resources that were mentioned in the ARENA curriculum. And one of the resources to learn more about Einsum was this blog, Einsum is All You Need. I will also link this blog in the description and highly recommend you to go through it to learn about Einsum in detail. So without further ado, let's look into the examples that were mentioned in that notebook. So Einsum can be implemented in NumPy via np.einsum, in PyTorch via torch.einsum, and in TensorFlow via tf.einsum. And today we will implement Einsum using Torch. So let's start with how a sum of a matrix will be calculated using Einsum. This is the notation we will use. Before that, let's understand what is happening here. So this first line basically shows a function that generates a one-dimensional tensor with values from 0 to 5. The 6 here indicates that this is the n value and starting value is 0. Reshape 2, 3 basically reshapes a tensor into a new dimension. So here 2, 3 means that the tensor will now have 2 rows and 3 columns. So reshaping allows the data in tensor to be structured in a way that is useful for further operations, such as matrix multiplications or basically like feeding into a neural network layer. So this is our tensor A, and this is the sum of all the matrix elements. So let's talk about this notation here because it's really important to understand it. Here I and J are typically used to denote the rows and columns of a matrix respectively. And whatever comes after the arrow here basically tells the Einsum instruction to sum over all the elements in that dimension. But as you can see here, there is nothing after the arrow. So no indices after the arrow means that this is going to sum over all elements of the tensor now. And the result is going to be a single number, which is the sum of all elements in the matrix or tensor A. And that's how we see the value 15 come up here. So in column sum, obviously, we are going to give the value j here because we want the answer to be the sum across all the columns. And this is the result that we get because as you can see, the answer is 3, 5, 7, which comes from this column addition of 0 plus 3, 1 plus 4, and 2 plus 5. That's why we get this value. Similarly, for getting a sum across row, now after the arrow, we will denote this I, which is going to give us a sum across all the rows. So 0 plus 1 plus 2 is equal to 3, and 3 plus 4 plus 5 is equal to 12, which is what we get. Now matrix transpose is pretty easy to understand because we're just reversing the indices, and this is the value we get. Now Now for matrix vector multiplications, what is happening here? So by only including I in the output, Einsum knows to sum over all the k indices that do not appear in the output specification. Thus, it performs a summation along the columns of A, multiplying each element by the corresponding element in B, then summing these products for each row separately. And that's why this is the result we get. And if you can recall, this is how the matrix multiplications work. So the resulting first index in the first row and first column of the result is going to be given by A1 into B1 plus A2 into B4 plus A3 into B7. And that is what we see here. So the common index between A and B is K, which means that for each element of the result, that is the output matrix, we multiply elements from A and B, where the second index of A, that is K in IK, matches the first index of B, that is K in KJ. And then we sum over K. And this is the answer that we get. For the vector dot product, I refers to the index over the elements of the vectors A and B. And the arrow with nothing after it indicates that we want to sum the element-wise products of A and B and return a scalar value, which is what we get. Now in the case of matrix dot products, Ij refers to the indices of two matrices A and B, both indexed by rows I and columns J, and the arrow with no indices after it means that the result will sum all the element-wise products into a scalar, which is what we see here. Now in the case of outer products, I refers to the index of the first vector A, J refers to the index of second vector B, and the arrow followed by Ij here means that the result should be a 2D matrix with the first dimension from A and the second dimension from B. And the outer product produces a matrix where each element is the product of one element from A and one element from B. And this is the answer that we get. And now let us understand what's happening here in the case of batch matrix multiplications. Here IJK refers to the first input tensor A, which is a 3D tensor with indices I, J, and K. And IKL here refers to the second input tensor B, which is also a 3D tensor, but with indices I, K, and L. Notice that the second index of the first tensor, that is K, is shared with the second index of the second tensor, which is K. And this is the index that will be summed over during the operation. So arrow followed by IJL specifies the resulting tensor's indices. So after the contraction, the output will be a 3D tensor with dimensions I, J, and L. And the index K is summed out during the contraction, leaving the remaining indices I, J, and L, giving us this value. Now we come to tensor contractions. So batch matrix multiplication is a special case of tensor contraction. So let's say we have these two tensors, an order n tensor A and an order m tensor B. For this example here, we have n equal to 4, that is order of A is 4, and m is equal to 5, that is the order of B is equal to 5. Now if you look at this carefully, I2 is equal to J3 because both of them are Q, and I3 is equal to J5 because both of them are R. So in this case, we can multiply the two tensors in these two dimensions, that is 2 and 3 for A and 3 and 5 for B, resulting in a new tensor C, which is given by this value. And this is the result that we get. So now that we have learned how to use Einsum for all these different operations, let's compare how efficient Einsum is as compared to a normal torch operation to do the same things. We will do this using the timeit library. So we are taking two really large matrices here for testing, and we are going to see how much time is utilized by both the Einsum and torch matmul operations. And as you can see, both of these operations are taking almost similar time, with Einsum taking slightly more time than the matmul operation. Now let's see what happens in the case of batch matrix multiplications. So as you can see, the Einsum here is taking lesser time as compared to the torch batch matrix multiplication function, which is indicating that when the computations get very complex, Einsum is going to be more efficient. So now let's dig into the Einops library to understand what these different operations are doing. So we are going to import some test images from the Einops library, which are basically these 6 images of size 96 by 96 with 3 color channels. So this is the shape of the IMS tensor here. And IMS 0 is going to be E, IMS 1 is going to be I, and so on. So firstly, in the rearrange operation, what we are basically doing is flipping the first index of IMS, that is E, in this way. So we are taking in the height, width, and channels and basically just flipping the height and width here, as you can see. Now let's look at how composition of axis can be performed. So basically, when we go from this BHWC into this version of batch and height as being a combined dimension, this is the result that we get, where we basically see the entire batch being visualized height-wise. So similarly, when we group the batch and the width, we are going to see the width-wise visualization of the entire batch. So what will happen to the shape of the tensor when we do this kind of operations of grouping the batch and width together or batch and height together, as we saw in this example? Basically, it's going to be a product of the components in that same dimension. So if we are grouping batch and width together, we will get 6 into 96 as the dimension for this group. So it's given by 576 here. And these are 4 dimensions, the batch, height, width, and channels. But when we convert them into 1D, the resulting array has as many elements as the original array. So that is given by this value here. Now let's look into the decomposition of axis. It is basically an inverse process where we are basically representing an axis as a combination of new axes. So when we set B1 is equal to 2, that basically decomposes the batch of 6 into B1 is equal to 2 and B2 is equal to 3. And that's what we get here. So the result will be now B being decomposed into 2, 3, and the rest of it remains the same. And we get this because when we say B1 is equal to 2, the batch size 6 is going to be decomposed into B1 is equal to 2 and B2 is equal to 3 because the product of 2 and 3 is 6. So basically this is showing the visualization of when we group B1 and B2 as this. So when we say B1 is grouped with height, which is the 2 being grouped with the height and the 3 being grouped with width, this is what we get. So E, I, and N are in the first row and O, P, S are in the second row. And this is the exact opposite of that grouping. So basically here B2 is grouped with height and B1 is grouped with width. And this is the visualization we get for that. So EIN becomes the first column now and OPS becomes the second column. So here we can also see that how we can squish the IMS tensor basically by moving the width dimension to the height. So when we say W2 is equal to 2 here, the width is going to be shrunk by 2. That means that when we group W and W2 together, the W here is going to be 48. Because if you remember, in our shape, W was equal to 96. So that's what happens when we group height with 2 and batch with 48. This is the visualization that we get, and we see the squishing effect here. So it's very important to note that the order of the axis matters when we are doing the grouping. So as we had seen earlier, when we group the batch with the width, this is the kind of visualization that we get. But let's say we don't follow the order. So instead of B coming before W, if W comes before B, this is the result that we get. So the order of axes in the composition is different. So remember to follow the rules as we do in the case of digits in the number. The leftmost digit is the most significant. We can also rearrange the ordering of the letters in different ways. So B1 and B2 are reordered before composing to width. So we basically have B1 and B2 here. And when we group B1 and B2 in this order, we get the Einops, which is the regular composition. But if we switch B2 and B1 here, this is the resulting combination of letters that we get. So E, O, I, P, and S. So we need to be aware of the order here. So that was all about the rearrange operation. Now let's understand what the Einops reduce operation is. So in Einops, basically remember that if an axis is not present in the output, it is basically reduced. So when we are basically reducing the batch height width channels to just height width channel, we have removed the batch. So it basically knows that we have to take an average over the batch and we use the mean operation here. So if we use the regular NumPy operation and calculate this IMS.mean here, it's basically going to be the same kind of visualization as this. So we can also reduce two dimensions at the same time. So basically reducing of several axes at the same time. So as you can see here, batch and channels are being removed here. So as you can see here, we no longer have like the brightness or color components. So we just have an average of everything, and that's grayscale. So we are left with height and width, basically meaning that we have averaged over batch and channels. And just like the mean operation, we also have different things like mean, max, sum, and product operation that we can do here. This is basically showing the mean pooling and how it can be achieved. So here H2 is equal to 2 and W2 is equal to 2, and H and H2 are grouped here and W and W2 are grouped here, but they are converted in this fashion. So here the batch and the width are going to be grouped. So this is the result that we get, where the image is basically split into 2 by 2 patches, and each patch is basically averaged because we are doing the mean operation here. And similarly, this is the max pooling operation here, given by this kind of a combination of dimensions. Now here what is happening is we are reducing over the channels. So basically you can see that the channels are not present here, and there is a grouping of B2 and height and B1 and width, and B1 is equal to 2. So all of the images now are grayscale, and that basically indicates that the channel dimension is reduced. Now in Einops, we can also do an addition or removal of axes. So we can write 1 whenever we want to create a new axis of length 1. And similarly, we can remove such axes. And this symbol here of open and close bracket is going to be a composition of 0 axes, and it has a length of 1. Now what's happening here? So this part here is basically computing the maximum value in each image across its height and width for each channel. And then it subtracts these maximum values from the original images to highlight the differences. Finally, it rearranges the images, laying them out side by side along the width dimension, because batch and width are combined here. So this process is useful for visualizing differences in the pixel intensities between images in a batch. Now let's look at the repeat operations in the Einops library. By writing it in this manner, we can basically repeat anything in this new axis, and this new axis can be placed anywhere. So let's say if we want to repeat E 3 times, this is how we will write it. So repeat widthwise, and repeat is equal to 3. So that's why E is going to be repeated widthwise 3 times. And if you want to repeat it along width as well as height, this is how we will write it. So here we will group 2 and height and 2 and width. And this is the resulting visualization. So again, as you can see here, the order really matters. When you change the order in these brackets and you put W before repeat, this is the resulting visualization that we get. So here it's basically repeating the width-wise pixels instead of repeating the entire image in the width dimension. That's why this order really matters. So we must prioritize the leftmost element here. Always remember that. So these are the main 3 operations in Einops: rearrange, reduce, and repeat. These 3 operations are really useful in a lot of applications For example, the rearrange is commonly used for ordering tensor dimensions such as converting between channels first and channels last formats in images. So it can also be used for tile images or combining image batches. The reduce is used to compress data such as calculating statistics like mean or maximum across different dimensions. Example, spatial pooling in convolutional neural networks. And the repeat is basically helpful for data augmentation, such as duplicating data points or expanding tensor dimensions for, let's say, broadcasting in neural network layers. So this was the case for images. But in transformers, in attention mechanisms, rearrange can be used to reshape the input into multiple heads or split inputs into queries, keys, and values for multi-head attention. Reduce can be used to collapse attention weights along certain dimensions, example to average attention scores. And repeat can be used for duplicating learned embeddings across sequences or expanding weight tensors for broadcasting attention calculations. Don't worry if you don't understand the meaning of these, we will understand them in detail in the upcoming sessions. But I just wanted to share how these Einops operations can be really helpful in manipulating the data or the experiments that you're going to run tomorrow. That's all for today. We understood the importance of using Einsum and Einops to make our codes basically more efficient and more readable and easy to debug. And these libraries are definitely going to help us tomorrow when we are going to do some serious mechanistic interpretability research. And now that we have covered all the important prerequisites, I hope that you are excited to dive into the neural networks, the different algorithms, the different models, and trying to understand how transformers work and how backpropagation works and what different hyperparameters are and how we are going to play with all these things to grasp what the neural networks are doing. So see you in the next episode for all these and more. Definitely check the description for all the links that I mentioned through this episode. And also, I'm going to share a link to the exercise that is going to help you practice Einsum and Einops operations. So that's all for today. See you in the next episode. Cheers.